Hello. Hello. Hello.
Yes, sir.
Okay. I'm sending this PDF notes. I will to explain. So my notes you have to prepare. Yeah, all the questions will be covered by these then previous question papers also. So all of you only class will be attended. My verify the PDF notes. Anyone doubts? Okay. Now.
Sir, please send notes.
Okay. Sure.
Okay, sir.
Hello.
Yes, sir.
Okay.
Yes, sir. Hello.
Okay. I'm so share screen.
Okay, sir.
Okay. This is my notes open. The topic is page number. Page number 53, Unit 5, Continuity and Compactness and Connectedness. Unit 5. All of you are textbook open. Okay.
Yes, sir. Yes, sir.
This is the 53 is a normal introduction. 54 in page number 5.3.1. Page number 5.3.1. So first we have the definition. This is the definition is continuous function. What is a continuous function? This is a BSc level or intermediate level continuous function. Same thing. Limit extends to a, f of x is equal to f of a. I think that is called as a continuous. This is a symbolically. So what's our definition? It is called this. We learn in PG metric spaces. So what is a metric space? X comma D is a one metric space. Y comma rho is second metric space. Actually, your textbook is X comma D1, one metric space. Y comma D2, second metric. X comma Y are two metric spaces. D1, D2. I am take now. This is X comma D, one metric space. Y comma rho is second metric space. Two metric spaces. So E is subset of X. E is subset of X. And small p be a limit point. Limit point. This is a limit point in E. Limit point in E. Be a limit point in E. So the function, what is the now? X comma D, one metric space, Y comma rho, second matrix, E is subset of X. What is the X is? Metric space. E is a subset of X. Indirectly, subset of X. And P be a limit point in E. Indirectly, what is now? P is also limit point in X. So actually, this is X is a metric space. He is subset of X. P is a limit point of E. Indirectly, P is also limit point of X. So if the function f is mapping from capital X to Y. What is the X is? One metric space, D. Y is second metric space. It is row. Your textbook is X is a metric space D1, X comma D1 one metric space, Y comma D2 is second metric space. Is said to be continuous function. Is said to be continuous. Is said to be continuous. Ekkada is said to be at continuous at P. P is a point. The P is a belongs to E. What is the E? Subset of capital X. What is F is a mapping from capital X to Y. Is said to be continuous at a P. P is a point. P be a limit point of E. And directly P is a limit point of X. X is domain. X is domain. Is said to be continuous. Is said to be
Excuse me.
continuous. Madam.
సార్ స్క్రీన్ కనిపించట్లేదు
అసలు కావట్లేదు, అనిపించలేదు. ఒకసారి చూడండి. సో నేను వైట్ స్క్రీన్ మీద చెప్పమంటారా? నోట్స్ మీకు అలాగే ఉంటుంది. ఒక వైట్ స్క్రీన్ PDF 4 ఉంటుంది, తీసుకొని చెప్తాను. చూడండి. సో దిస్ ఇస్
కనిపిస్తుంది సార్.
కనిపిస్తుంది ఇప్పుడు? ఓకేనా? యాక్చువల్ మై సెంటెన్స్ నోట్స్ ఇస్ దే. సో యాక్చువల్గా ఐ విల్ టేక్ ఆల్సో అదర్, ఇంకొకటి తీసుకుంటాను. ఇప్పుడు వైట్ స్క్రీన్ అవపడుతుందా మేడం? యా, వి నో వైట్ స్క్రీన్.
ఎస్ సార్.
ఓకే. చూద్దాం ఎంతమంది అటెండ్ అయ్యారో చూద్దాం. ఇప్పుడు జస్ట్ 16 మెంబర్స్ వచ్చాయి. 16 మెంబర్స్ ఉన్నారు, నో ఇంక్రిమెంట్. సో ఇప్పుడు ఒక వైట్ స్క్రీన్ అవపడుతుందో చెప్తాను చూడండి. సో ఎక్స్ కామ డి వన్ మెట్రిక్ స్పేస్, వై కామ రో ఈజ్ సెకండ్ మెట్రిక్ స్పేస్. ఈ సబ్సెట్ ఆఫ్ ఎక్స్. ఓకే. సో P is element of E, B is a limit point. F is a function from X to Y. E is said to be continuous. 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 Okay. Ekkada at P, it's said to be continuous at P. Same. Said to be continuous at P. So this is a same ade page lo vartundi. Second page kada. Is said to be continuous at P. అర్థమైంది? All of you, X comma D one metric space, Y comma row second metric space, E subset of X. P is element of B, be a limit point of F is a mapping from capital X to Y. Is said to be continuous at P. What is the definition? So this is the definition. So given epsilon greater than 0, there exists delta greater than 0, such that row of at second metric space, row of f of x comma f of p, so is less than epsilon. So when d of x comma p is less than delta, d of x comma p delta, and x is belongs to p. This is the definition is called as second row. That is called as the second row. F of x comma f of p is less than epsilon, or d of x comma p is less than delta. Then function f is said to be continuous. Okay. So this is a said to be continuous. Okay. Now it is a said to be continuous definition. What is a continuous definition is? This is a definition. Go to run. What is now? One is x comma d is a metric space. Y comma row second metric space. This is a x comma p is a limit points anukunte ikkada mapping is etlunte this points f of x f of p. This is f of x f of p. So what is the definition here? Chudandi, d of x comma p is less than delta aithe implies f of x comma f of p etlundale, that is a row of less than epsilon. That is a simple definition. Dx comma, the distance of x comma p is less than epsilon. This implies a row of f of x comma f of p is ikkada delta. So less than delta. This is less than epsilon అయితే then f is mapping from capital X to y is continuous function. F of x to continuous. What is a continuous function definition? This is a continuous function definition. Okay. So the continuous function definition. Now again, the continuous function definition f of x. Now this is continuous function definition. So it is same thing. Note 1. F is said to be continuous on E, then F is continuous at every point of E. If P is any point of at P, then P is either limit point or isolated point of E. Take F is mapping from. So this is F is mapping from X to Y is said to be continuous. Continuous on E. On E is means E is subset of X on E. So then F is continuous at every point. So at every point of E, every point of E. So then P is any point of E, then P is either limit point or P is isolated point. So second, if F is a limit point of E and F is continuous at P, what is the point? What is the definition? Intermediate level definition. Limit n tends to infinity, f of x is equal to f of p. F of x is equal to f of limit n tends to infinity, f of x is equal to f of p. This is the definition. So we called is the definition is this is a definition. Okay. So now in textbook is 5.3.1 theorem. In page number, it is also the page number is 54. 54 page number is, what is the 54 page number? 5.3. F is mapping from capital X to Y is continuous function on a compact metric space X. X anadi compact metric space అయితే, compact metric space అయితే, then f of x is a compact. ఎక్కడ? This is a compact in Y. Compact in Y. So దీన్ని ఏం చెప్తాం? A continuous image of a compact metric space also compact. నా నోట్స్ లో ఇచ్చాను సెంటెన్స్. F is mapping from X to Y is a continuous compact metric space X, then f of x is compact in Y. Is compact. Therefore, F is mapping from capital X to Y. X is compact. This is compact. Then f of x is also compact. Whenever the image in compact in Y, the image is in compact. This image inkemanachchu. Therefore, this theorem is also other sentence. A continuous image of a compact metric space. A compact metric space is compact. So this is the theorem proof. So have to tell me proof theorem statement. Chudandi 5.3.1. Already my PDF notes are the same thing. So this is a very simple X. So Y. So this is X. Is F is mapping from. So this is compact. I think this is image. The image is f of x is always subset or equal to Y. Since X is compact. So already in condition, F is mapping from capital X to Y is continuous. We show that f of x is a compact in Y. So what Uma kodebo lulekuna sunvandi. Uma please. So this is let G of alpha such that alpha belongs to I. Be a open cover. Compact set be an open cover. Be an open cover for f of x. Be an open cover for f of x. To show that f of x compact chunchalante, this compact set will be, it is a open cover. So be a open cover f of x. This f of x, a sentence, a matrix space set to be compact, is containing a finite open cover. This is union of alpha belongs to I. This is a G alpha. Where is each G alpha is a open set. Each G alpha is a open in Y. Open cover until this is a open cover. So this is we have to prove. And what now? Where? Like actually what happened? F of x in subset are called union of I. Alpha belongs to I. This is G alpha. Where? So G alpha such that alpha belongs to I is an open set. Is a open set in Y. Is a open set in Y. So open set in Y. Already we know that f is mapping from x to y is continuous. Continuous అయితే then f inverse of g of alpha ఏం కావాలి? It should be is open. అంటే f of x is open, g of alpha is open in y అయితే inverse of g alpha is open in y. F inverse of g alpha is open in ఎక్కడైతే కంపల్సరీ ఇన్ ప్రీవియస్ థియరం open in x for every g alpha. So this is very simple. F inverse of actually f is mapping from x to y is continuous. So this is g alpha is open in y అయితే so f inverse of g alpha అనేది compulsory is open in x. ఇది already starting theorem. Already I will tell in the class in board also. Every g alpha is open in y. So open in y. Inverse of a g alpha is open in x. So open in x. So what is the equation 1? Equation 1 already I am taking. What is the equation 1 I am taking? F of x is subset R called union of alpha belongs to I. This is a g alpha. F is going the right side. So this is equation 1. Right side అయితే x is subset R equal to f inverse of union of alpha belongs to I. This is a g alpha. X is subset R equal to union take outside. You alpha union of I belongs to I. F inverse of g alpha. So f inverse of g alpha. This is called is from third equation. Second equation into the f inverse of g alpha is open in x. X is subset. F inverse is open cover for x. F inverse of this is f inverse of g alpha is a open cover for x. This is a clearly f inverse of g alpha is an open cover for x. So since x is compact, so x is compact, there exists ఒక కాంపాక్ట్ డెఫినేషన్ ఏముండాలి? x is compact అంటే two definitions. One definition is closed and bounded. Other definition is a set is said to be compact if it has a finite subcover. If it has, so there exists a finite cover ఉండాలంటే what is now? There exists a finite subcovers. So there exists a finite subcover, a finite. So compulsory. So f inverse of g alpha is, so in previous part is this is f inverse of g alpha is open for x. So x compact కాబట్టి, so this is x is a finite subcover. What is the subcovers? F inverse of g alpha 1, comma, f inverse of g alpha 2, comma, f inverse of g alpha n. So that is such that ఏమొస్తుంది 100% x subset r equal to union can write here. F inverse of g alpha 1 union f inverse of g alpha 2 union up to so on f inverse of g alpha n. So g alpha n. X is subset R called f inverse is common. Up to what is g alpha 1 union g alpha 2 union up to so on union g alpha n. So this is clear. So F inverse is take right side. And what is now? This is X is subset or equal to F inverse of G alpha 1 union G alpha 2 union up to so on union G alpha n. So F of X so is subset or equal to G alpha 1 union G alpha 2 union up to so on union G alpha n. So G alpha n. So G alpha 1 G alpha union is called is the set is what is the set is G alpha 1 G alpha 2 up to some G alpha n is a finite subcover for f of x. A set is said to be compact. It has a finite subcover. F of x is a finite subcover. What is a finite subcover? G alpha 1 G alpha 2 G alpha n is a finite subcover for f of x. Hence the theorem, hence f of x is a compact. F of x is a compact. So this is a theorem is closed. What is the theorem is 5.3.1 theorem. 5.3.1 theorem is, so I'm telling me. So first one, x is a compact term taken, continuous condition taken. We have to prove. We have to prove is f of x is continuous. Okay, compact we have to prove. This is the 5.3.1. So is complete. So I'm telling me definition is the next definition. We know already, we know well definition. It's now, it is a bounded definition. So what is a bounded definition is, this is BDD, bounded. Bounded definition is called is, suppose F is mapping from capital X to Y is a, it be a metric space. So metric space. So a subset is a subset of a metric space X. So into a real number system equivalent R power of K. F is said to be bounded. This is a bounded. There exists a positive constant M. There exists a positive M greater than 0 such that f of x. So mod f of x is less than or equal to capital M. So for all x is belongs to, and also this is f is mapping from capital X to Y be a metric space function is subset or equal to capital X. So metric space into this is a real number system R power of K is said to be bounded if there exists a positive number M greater than 0 such that mod f of x is less than or equal to capital M for all x is belongs to M. So that is called is a bounded definition. Okay. So bounded. What is a f is mapping from indirectly? Is subset of x tends to R power of K. This is a function. Is said to be bounded. So bounded column is mod f of x less than or equal to n. Bounded it is called, a function is said to be bounded. It has lower bound or upper bound. Okay. So this is whenever you are so many 18 numbers are there. Now, so once again, okay. So this is called is. So next to theorem 5.3.2. What is the 5.3.2 theorem is? So f is a continuous function compact to metric space x into R power of K. F is a continuous mapping. And f is mapping from capital X to compact to metric space to R power of K to function. Then f of x. In inshallah we have to theorem. Then f of x. Then f of x is closed and bounded. Closed and bounded. This is a closed and bounded proof. This is the theorem 5.3.2 theorem proof. So we have to 5.3.2 theorem proof by using like that. So 5.3.2. Next is now is a bounded definition. So it's a clearly. So this is a bounded definition is a clearly chosen proof. So I have to taken. So this is called is x is one metric space. R power of K another, this is a Euclidean space. 2 is a function f of x. So this is a capital X we have to prove capital F of X is bounded in R power of K. Since F is continuous, F is continuous mapping. Defined on a compact metric space. A compact metric space. A compact metric space. A compact metric space. X into R power of K. X into R power of K. Compactness. We know that continuous image of a compact set is compact in previous theorem. F is continuous defined his in set to his compact type, then F of X is in previous theorem. Continuous image of a compact metric space is compact. Then previous theorem, capital F of X is compact. This is image in previous theorem, compact. So compact. So hence compact subset of R power of K, subset R power of K, the compact matrix. But we know that. So compact subset of R power of K. Compact subset of R power of K already undi. This is compact subset of R power of K if and only if in previous, if and only if it is bounded and closed. A compact at the R power of K bounded and closed. So hence, so this is we know that F of X is compact R power of K, it is a bounded hence. Hence, what happened is hence capital F of X is closed. This is closed and bounded. This is bounded in R power of K. In R power of K. So since the range of F of X of F is bounded, so we get is F is bounded. So we get F is bounded. F is bounded. So we get is F is bounded. So this is the theorem is completed. Once again, what is the theorem is 5.3.3. So F is a continuous mapping compactness in R power, then F of X is closed and bounded. Yes. No matter we know that F is mapping from X2 into R power of K is a compact metric space. This is continuous compact metric space. I think previous theorem, capital F of X is bounded into bounded in subset of bounded subset of in R power of K. I think if and only if it is closed and bounded. Because this is F of X is automatically is a closed and bounded also. This is 5.332 is completed. So next is 5.33. So if F is a continuous real function, if F is a continuous real function on a compact metric space X, F is a continuous real function, a compact metric space X. F is a continuous metric. F is a continuous, a real function, a compact metric space X. So metric space X, it is called this. So this is called. So what is the 5.5 theorem statement is? So compact metric space X, if M is equal to LUB, least upper bound. X is small x is belongs to capital X, F of X, least upper bound. Okay. Then you have supremum of F of X in small x is belongs to capital X. Okay. Small m is equal to least upper bound, greatest to lower bound, GLB of F of X in small x belongs to capital. GLB is meaning infimum of F of X is belongs to capital X. What is a capital M is equal to supremum of F of X is a small x is belongs to capital X, or least upper bound of F of X LUB, small x belongs to capital X. Same, small m is equal to infimum of F of X is equal to small x belongs to capital X. Same thing, greatest to lower bound of F of X is small x belongs to capital X. What is the greatest lower bound? What is the least upper bound? Okay. So చూడండి, So we learn in a real number system. So S is subset of R. In small x is belongs to R. So then U is belongs to R is said to be upper bound. L is x is less than or equal to U. For all x belongs to U, x belongs to S. Then U is called as an upper bound. What is a real number system here? S is subset of R. U belongs to R. X is belongs to S. X is less than or equal to U for all x belongs to S. Then U is called as an upper bound. So what happened is x is less than or equal to U is less than U plus epsilon is also upper bound. U plus epsilon is also upper bound. X is less than or equal to is less than U plus epsilon is also upper bound. Then U is called least upper bound. It is BSc level question. Is called least upper bound. U is called least upper bound. The least called is least upper bound. It is called supremum of S. Supremum of F name least upper bound. Okay. We learned discussion is same thing. A real system or S is subset of R, X belongs to R and small a. L is less than or equal to X for all X belongs to S. Then L is called as a lower bound. Then L is called as also lower bound. L minus epsilon is less than L is less than or equal to X for all X belongs to S. Then L minus epsilon is also a lower bound. Is also a lower bound. So then L is called as greatest lower bond. It is denoted by infimum of S. Infimum of S. It is denoted by infimum of S. Infimum of infimum of S. So L minus epsilon is also lower bond. Then L is called is the greatest lower bond. It is denoted by infimum of S. Ikkada we learn is capital F is equal supremum of F of X and of a for least upper bound of F of X is belongs to X belongs to capital X. Small m is equal to infimum of F of X and the same thing. It is also greatest lower bound of F of X in small x belongs to capital X. So what is the what is the small m is called is the greatest lower bound. What is the capital M is called is least upper bound. So this is the question. So what is the question is 5.3.3. A function f is continuous real function of a compact vector space X. M is equal to least upper bound of F of X. Small m is equal to greatest lower bound of greatest lower bound of F of X. Then there exists P comma Q 2 points. P comma Q belongs to capital X such that F of P is equal to attains capital M. F of Q is equal to attain in small m. So that is meaning F of Q is less than or equal to F of X is less than or equal to F of P. What is F of Q? Small m is less than or equal to F of X is less than or equal to capital M. What is the small m is? Infimum. What is the capital M is? Supremum. I think this is a theorem. This is attains from. Whenever F is continuous function, continuous compact vector space, I think, then F is attains bounds. Attains bounds is meaning lower bound or upper bound. Lower bound it is called is least upper bound, or greatest lower bound. Upper bound is called least upper bound, supreme. So this is the theorem. So I have to theorem proof is in previous theorem using 5.3.3. So by using the application, so that is the theorem. So children, proof. So this is the only theorem statement I have to explain. We have to go to the theorem proof. What is the theorem proof is? If f is a continuous real function, since f is a continuous real valued function dependent on compact vector space, f is a real valued. So f is a real valued continuous compact vector space X. F is continuous. F is a continuous real valued. So real valued. And compact vector space. We know that f of X is ante. What is the function? F is a mapping from X to Y and simple. So then F is a real valued. So real valued continuous compact. This is a compact vector space in X. In previous theorem starting previous theorem 5.3.6 So this is the starting theorem is called is 5.3.1. So our theorem in this is capital F of X. It's a image is also is also compact. Is also compact. Is also compact. This is also compact. So every compact set and also every compact set also and also closed and bounded. Closed and bounded. A closed and bounded also. So closed and bounded. So a closed and bounded subset of F is mapping from X to Y is continuous. X is compact. So in compact, F of X is also compact. Is also compact in Y and is also compact and also and we know that also we know that WKQ. So and we know that and F of X is also capital F of X is also F of X is also closed and bounded. Closed and bounded. So closed and bounded subset of or subset of closed and bounded subset of R. So closed and bounded subset of R. Next we can discussion is small m and capital M. What is a small m? Infimum. This is a small m is equal infimum. What is a supremum is equal? A capital M is equal supremum. Infimum and supremum of small m and capital M. Infimum and supremum of F of X. Of F of X in our real number system. What is now? Small m and capital M, infimum and supremum of F of X in R. F of X in R. So F of X in R. So that is F of X in R. That is called is small m and capital M, infimum and supremum of F of X in R. That is small m is equal to, we can do right here. So GLB, greatest lower bound of small x belongs to capital X into F of X. Capital M is equal to supremum anakate or least upper bound of F of X is belongs to small x belongs to capital X. Greatest lower bound and least upper bound. The greatest lower bound, its name is infimum. The least upper bound is called is supremum. So this is in since F of X. Nothing else. Since F of X is closed. Since F of X is closed in R, F of X is closed in R, we get that. So we get that. Small m and capital M is belongs to F of X bar is equal to F of X. X bar, F of X is equal to F of X bar. So this is the derived set. So there exists a points P comma Q is belongs to capital X such that F of P is equal to small m, F of Q is equal to capital M. F of P is equal to small m, F of Q is equal. So F of P is equal to F of P is equal to F of P is equal to capital M, F of Q is equal to small m. So we like that. So in fact, in the small m is less than or equal to F of X less than or equal to capital M. Small m is means F of Q is less than or equal to F of X is less than or equal to F of P. So that is a F of P is also. Small m is less than or equal to, so that is called is F of Q less than or equal to F of X less than or equal to F of P. So that is called is, hence F is, so this is the lower bound, upper bound. A set function is said to be lower bound or upper bound is called is bounded. So then since F is bounded, and attains its bound. So it's bounded. Okay. And attains its bounds. So this is the theorem is closed in 5.3.3. So 5.3.3 is closed. Next is 5.3.4. The theorem is not important, not given and proof. So if it is any question paper ask reverse, I will tell you also. Next we are go to the definition. 5.3.5. What is a 5.3.5 definition is homomorphism. So what is a homomorphism is a function is f is x to y is continuous function, continuous bijective function is continuous. So continuous bijective function, then x into metric space y, then F inverse is also. So F inverse is continuous function. So the inverse function, so y to x is also is also continuous, is also continuous, is called is homeomorphism. Homomorphism కాదు, homeomorphism. So f x tends to y continuous, inverse is also y to x is also then it is also so is called is a homeomorphism. Next definition is uniformly continuous definition. This is a uniformly continuous definition is. So what is a uniform continuity? Already I am telling me in the board, physical classes. So uniform continuous. So again, now uniformly continuous, uniform. So this is, so uniform continuous is called is, so this is I am to this is uniform continuous. This is a uniformly continuous. What is a uniformly continuous? Uniform continuity. Suppose x comma d1, one metric space, y comma d2 is second metric space, b2 metric spaces, f is mapping from capital X to y. So is said to be uniformly continuous. So ఇక్కడ చూడండి, I'm to tell me. So white pages is also clear.
Sir, this is also clear.
Clear na? Okay na? So atlaithe I have to tell me, no problem. Okay. So this is uniformly continuous. X comma d1 one metric space, y comma d2 two metric spaces. F is mapping from. What is F is mapping from? So F is mapping from. So this is F is mapping from capital X to Y. What is X is one metric space, X comma d1, Y comma d2 two second metric space. It's said to be uniformly continuous. Uniformly continuous whenever continuous, uniformly continuous always on domain on X. If for each epsilon greater than 0, there exists delta greater than 0, such that for all 2 points P comma Q belongs to capital X. Okay, with D1 first metric space, D1 P comma Q is less than delta, implies D2. So f of P comma f of Q comma is less than epsilon. Okay, so D2 second metric space, D1 is called as first metric space, X comma D1 first metric space, X comma D1 first metric space P comma Q less than delta, implies X Y comma D2 half f of P comma f of Q is less than epsilon. That is called is uniformly continuous. It's a very simple. It is also shown. This is a two functions are there. So it is a clear. So the point. So it is a P comma Q 2 points. So this is a functions f of P comma f of Q. So X comma D1 one metric space, Y comma D2 second metric space. This is a function. It's said to be so called very simple. D1 comma P comma Q. D1 comma P comma Q is less than delta, implies D2 half f of P comma f of Q is less than epsilon. So this is the 2 points are, so f of P comma f of Q less than epsilon. It is called is a uniformly continuous. So this is the definition. This is the page. So what is a uniformly continuous is the definition is note one. Uniformly continuous defined on only set but not a points. Well, you have to points is the definition of only continuous. Continuous a continuous function defined that at a point, at a limit point. And what is a uniformly continuous? It is a defined hand, a set, a defined hand, a closed set, a bounded set, a defined hand. Uniformly continuity is a defined hand only set of but not points. Second note. Uniformly continuity అయితే implies continuous, reverse is not wrong. Ante this is every uniformly continuous is continuous function. Every continuous function is need not be uniformly continuous. That can give the example in proof. So ikkada ichchanu. So what is a uniformly continuous? Uniformly continuity of a function implies continuity. Example, suppose f of x comma y is uniformly continuous. To each epsilon greater than 0, there exists delta greater than 0 such that p comma q is belongs to capital X. With the definition emandale, first d1 of p comma q is less than delta implies d2 of f of p comma f of q is less than epsilon. This is the equation 1. Small p belongs to capital X. Then above small p belongs to capital X. Then above limits, they obey implications. What is the implications of all this? So you can d1 of x comma p, d1 of x comma p in points implies less than delta implies if and only if d2 of f of x comma f of p so is less than epsilon, then f is continuous. A continuous, one point is set, one point is a point. So f is continuous at a point. F is a continuous at a point. F is a continuous at point. P belongs to x is a arbitrary point. So then f is continuous on x. Continuous definition undalante d1 of x comma p 1 point to less than delta implies d2 of f of x comma f of p small x comma p. This is implies less than epsilon, then f is continuous at p. So p is arbitrary point, f is continuous on x. Remember, converse is not true. The converse of the theorem is not true. This is the example is the converse of the above the problem is not true. So the above statement is may not be true. Define a function. So what is the define function? The function 1 comma 2 open close, this is implied to real number. F of x, iదే టెక్స్ట్ బుక్ లో your example also 1 by x minus 1. Your టెక్స్ట్ బుక్ లో అయితే what is the example is 1 by x minus in page number example లో లాస్ట్ ఉంటుంది. That is the example of 56 లో, that is the example 1 by x minus x1. Your టెక్స్ట్ బుక్ లో 1 by x minus x naught ఉంటుంది. So 1 by x minus 1 is a wonderful. So that is called is a belongs to 1 comma 2 open closure is always continuous. Every polynomial function is a clearly, this is a polynomial function is clearly f is continuous. F is continuous on interval. So 1 comma 2 close interval continuous. Suppose f is uniformly continuous, this interval check them. So this is interval check them is called this. So what is the check them? X1 comma x2 2 points. X1 comma x2 2 points is so 1 comma 2 closure అయితే implies mod x1 minus x2 is less than delta implies mod of f of x1 minus f of x2 is less than epsilon. So this is the equation. We have to verify. So this is a verify equation 1. So I am to clear. No. This is now again. Now choose, this is a I am to choosing. Now choose delta dash is greater than 0 such that delta dash less than or equal to delta and 1 plus delta dash by 2 power of n greater than 1 plus delta dash by 2. So is always belongs to 1 comma 2 open interval for all n. In taking x1 is equal to 1 plus delta dash by 2 power of n, here x2 is equal to 1 plus delta dash by 2 only. X1, x2 decide just choose. Mod x1 minus x2 I have to verify. So this is called 1 plus delta dash by 2 power of n minus 1 minus delta dash by 2. So if minus 1 plus 1 is cancelled, this is delta dash by 2 power of n delta dash by 2. So this is always delta dash by 2 power of n plus delta dash by 2. So we call this always, this is equal to always less than delta dash is less than or equal to delta, less than delta. So Koti, we have to choose x1 minus x2 is less than delta, verify. So next to verify is f of x1 minus f of x2. We have to verify. So this is f of x1 and what is x1? x1 minus 1 minus x2 minus 1. So this is the point. What is the x1, x2? So I am choosing also. One first to check them. 1 by x1 minus 1. 1 by 1 plus delta dash by 2 power of n minus 1. Minus 1 plus 1 is cancelled. Nothing but 2 power of n by delta dash. Same thing, 1 by x2 minus 1. What is the x2 point? 1 by 1 plus delta dash by 2 minus 1. Plus 1 minus 1 is cancelled. 1 by delta dash by 2. It is called 2 by delta dash. Okay. This is a totally equation is second. I am to totally question second. So now it is a mod of f of x1 minus f of x2 is a verified is equal to, what is the result is 2 power of n by delta dash minus 2 by delta dash. So this is always. So delta dash is LCM got 2 power of n minus 2 also. So we got always. This is mod f of x1 minus f of x2 always. The right side is part is always greater than epsilon, not a epsilon. For r large n, this is a contradiction to equation 1. So hence f is not uniformly continuous than example. So this is a problem. So next is a theorem is, so the theorem proof is, so in 5.3.6 in same page number, same page number 54, in page number 54, we got is 5.3.6 theorem statement. F is continuous, a mapping, a metric space x into another metric, then F is uniformly continuous. Ante em ikkada F is mapping from x to y is continuous metric space aithe. What is a continuous compact metric space? Continuous compact metric space aithe, then F is uniformly continuous. F is uniformly continuous on x. Uniformly continuous on x and proof. Actually, general kaadu. Every uniformly continuous is continuous x. Every continuous is need not be uniformly. Give the example explanation. But whenever it will be taken, one set is f is x to y is a continuous compact metric space. Then f is uniformly continuous on x. Uniformly continuous x and proof. So f is uniformly continuous x and chunchal. So this is a theorem statement. 5.3.6 in page number 54, last theorem down. So I have to not proof in textbook model. So we have to clear now. So this is a theorem is, let f is mapping from. So this is a f is mapping from. So what is a f is a mapping from? X comma d1 one metric space, y comma d2 another metric space, be a continuous. So f is mapping from. So f is mapping from x comma d1 one metric space to y comma d2 second metric space, be continuous. So be continuous. Indirectly it was simple, right? F is mapping from x to y, be continuous. X is compact. X is compact. X comma d1 compact. So compact definitely let epsilon greater than 0 by given. So let x be any arbitrary point. Let x be any arbitrary point of x. Let x be any arbitrary point of x. Since f is continuous, at x. So what you have to tell me? So since f is continuous at x, the definition continuous x definition is I'm taken. So what is the continuous definition is? I'm taken 2 points. So that is d1 of x comma y implies delta x implies d2 of f of x comma f of y is less than epsilon by 2. దట్ ఈస్ ద ఈక్వేషన్ 1. సో మీకు ఫ్రెష్ పేజ్ మీద చెప్తాను చూడండి. సో వెరీ so this is called as first f is what now is f is mapping from x to y is a continuous, x comma d1 is a compact, so compact security. So what is the continuous definition is d1 of x comma y is less than delta x. This implies d2 of f of x comma f of y is less than epsilon. These are equation 1. The set sx comma delta x by 2, sx comma delta x by 2 such that small x belongs to capital X. Behind open spheres, open spheres is an open cover of X. Open sphere of open cover of X. Behind open spheres is an open cover of X. Since this is the continuous definition of open sphere, like actually it's also is there. Since X is compact definition చెప్తుంది, there exists a finite subcover. What is a finite subcover? S of x xk delta x by 2. So in such that k is equal to 1 comma 2 comma n. So such that x is equal to finite subcover union of this is s of xk comma delta xk by 2 k is equal to 1 comma 2 comma n అంటే finite subcover in second equation. So second equation ఎట్లున్నా చూడండి, x is equal to union of this is a open sphere delta x xk. So this is small xk. So sorry, now x is equal to open sphere union of s of xk comma delta xk by 2 such that k is equal to 1 comma 2 comma n. So this is equation number 2. So delta is equal to a minimum of, what is the minimum of delta x1 by 2, delta x2 by 2 up to so on delta xn by 2. So delta greater than 0. Let x comma y two arbitrary points of x comma y two arbitrary points means small x comma y is belongs to arbitrary points I am taken. d1 of x comma y is less than delta x by second implies x is belongs to s అయితే, so x is belongs to xk delta xk by 2. So that is in fact that em raskochu we like that d1 of x comma xk is delta xk by 2 less than delta xk. So d2 of this is a d1. So of whenever f of x comma f of xk is less than epsilon by 2, we are from third. Triangular inequality using d1 of y comma xk is less than or equal to d1 of y comma x plus d1 of x comma xk. So this is a less than delta and also plus less than delta xk by 2. And minimum నుంచి also minimum delta is equal to delta of xk by 2 plus delta of xk by 2. So ఈ రెండు delta of xk by 2 is equal to 2 delta of x by 2, 2 is cancelled, delta of xk. This is equation number 4. So equation ends from first equation. So this is called is a first equation. This is from first equation. So d2 of f of y comma f of y comma f of x k is less than epsilon by 2. d2 half నేనేం తీసుకుంటున్నా f of x comma f of y is a triangular inequality of s of d2 half f of y comma f of x comma f of xk. So plus d2 half d2 of f of xk comma f of x. So ఈ రెండింటి నుంచి from third and fourth from third and fourth is less than epsilon by 2 plus epsilon by 2 is equal to epsilon. So that's called is from third and fourth we got. So what is third and fourth we got result is d1 of x comma y is less than delta implies d2 of f of x comma f of y is less than epsilon. So less than epsilon. So less than epsilon for all x comma y is belongs to capital X, 2 points. So therefore, hence f is uniformly, so uniformly on x, uniformly on x. Textbook lo unna time proof avasram ledhu. Mee cheppina notes prakaram kuda clear unte we got the marks also. So I have to taken once again in the notes is also like that. So now it's a clearly. So I have to explain. So uniformly continuous. So this is a theorem. This is a theorem 5.3.2. E is a uniformly continuous. This is called. So this is 5.3.16. F is I have to take a second equation, first equation, and third equation, fourth equation. By using third and fourth, we got is I have to explain F is uniformly continuous. So that is called this. So F is uniformly continuous. Next is, so this is called as connected set. So what is a this is a 5.4.1 theorem. 5.41 theorem is a connected. A continuous image of a connected set is connected. So continuous image of a connected set is connected. So this is F is continuous in previous part. F is continuous, x tends to y is a continuous. X is compact, then f of x is also compact. Y is the reverse. F is mapping from x tends to y. X is connected, connected set to connected. Then f of x is also connected, connected. So that is a connected. What is a connected set is? This is that. It cannot be written as the union of two designs non-open sets. Designs non-open sets cannot be written as union of the two designs open sets. It is a connected. What is the disconnected? Can be written as the union of two designs open sets. Can be written as union of two designs open sets is called this not a connected. Connected cannot be written as union of two designs open sets is called as a connected set. So that is f x tends to y is a compact. X is a connected metric space, then f of x is also connected metric space. A continuous image of a connected metric space is connected. A continuous image of a connected metric space is connected. So this is a theorem proof is also. So we got now again. Okay. So it's a clearly I have to explain this theorem is in proof. So what is the theorem is proof is I am to theorem is proof. It's a clearly now. So therefore, for suppose he is a connected in x. Okay, what is now? This is one is x comma d1 one metric space, y comma d2 another metric space. He this is f of e is a x E is connected. Then f of e is also connected set. Actually, x is e this. So f extends to suppose he is a connected in x. E is a connected set in x. Then f of e is connected in y and proved. So we claim. So what is now f is mapping from x tends to y is continuous. A claim proof f of e is connected. F of e is connected. F of e is connected. If it possible, I am to wrong sentence. If it possible, I am wrong sentence. F of e is not a connected. Not connected ko very simple example. Not connected example entity. What is the not connected is called is f of e is equal to a method can be written as union of a set is connected cannot be union of two designs open sets. What is a not connected? That can be written as union of two design sets. F of e is equal to a and b. What is f of e? Not a connected. Not a connected got a and b. N can be. What is A comma B? A is a non-empty set. B is also non-empty design sets. What is the design sets? Ante A intersection B is separated set. A complement intersection B is also intersection pi. Ante with nematam separated sets is separated. Can be written as f of E can be written as union of two separated sets. I think then f of E is not a connected. F of E is connected. That is the meaning is f of E can be written as a union of a two connected sets. What is a connected set? A intersection B complement is equal to pi. A complement intersection B is equal to pi. A comma B are two non-empty sets. So I have to taken. So this is called this. G is equal to, I have to taken. This is G is equal to E intersection F inverse. So I have taken G is equal to E intersection F inverse of A. So H is equal to em తీసుకుంటున్నాం E intersection F inverse of B తీసుకుంటున్నాం. ఇది గుర్తుంచుకోండి G and H. G is equal to E intersection F inverse of A. H is equal to E intersection F inverse of B. ఇక్కడ G and H. G and H are subsets of E. So we prove that G and H are non-empty separated sets in X. We prove that ఏం ఉంచాలి G and H are non-empty separated sets in X. We use a whose union is E. So that is whose union is E, that is a clearly. So that is clearly showing that he is a disconnected. So, okay. So okay. Showing that he is a disconnected, which can be written as so showing that he is a, which can be written as showing that he is a disconnected, which can be become a contradiction to our hypothesis that. So this is showing that this is he is a disconnected. So that is called is a disconnected, which can be become a contradiction to our hypothesis. A is a non-empty set. So f of E is equal to A union B. So E intersection F inverse of A is equal to G, a non-empty set. Similarly, B is also, H is also non-empty, B is also non-empty. F of E is equal to A union B. It can be written E intersection of F inverse of B is equal to H is also non-empty. So we prove that. This is prove that. So we prove that G is equal to. So we prove that G union of E is equal to H and E. So G union of H is equal to, we prove that G union of H is equal to E and H. So I am taken left hand side. X is belongs to G union of H. So therefore X belongs to G or X belongs to H. So what is the X is belongs to? What is X belongs to G and X is belongs to E intersection of tells, we know that F inverse of A. So or X is belongs to H and also E intersection F inverse of B. So I am to write here. So this is called this. So therefore X is belongs to E implies. So this is called this X is belongs to E. So X is belongs to E. What happened? So G union of E, G union of H is subset or equal to E in our form star equation. Suppose next time X is belongs to E, this one we have to prove X belongs to G union of H. So image apply and F of X is belongs to F of E. So therefore F of X belongs to F of E is a union B. X F not append X is belongs to F inverse of A union B. So therefore X is belongs to F inverse of A or union F inverse of B. సో దట్ ఈస్ ద ఎఫ్ ఇన్వర్స్ ఆఫ్ బి. ఇండైరెక్ట్లీ ఏం రాసుకోవచ్చు ఇక్కడ ఎక్స్ ఈజ్ బిలాంగ్స్ టు ఎఫ్ ఇన్వర్స్ ఆఫ్ ఏ యూనియన్ బి వచ్చేసింది. సో దీన్ని ఎక్స్ ఈజ్ బిలాంగ్స్ టు ఎఫ్ ఇన్వర్స్ ఆఫ్ ఏ ఆర్ యూనియన్ ఎఫ్ ఇన్వర్స్ ఆఫ్ బి. సో ఎక్స్ బిలాంగ్స్ టు ఇంకేం రాసుకోవచ్చు, వీ నో దట్ ఎఫ్ ఇన్వర్స్ ఆఫ్ ఏ ఆర్ ఎక్స్ ఈజ్ బిలాంగ్స్ టు ఎఫ్ ఇన్వర్స్ ఆఫ్ బి. సో ఎఫ్ ఇన్వర్స్ ఆఫ్ బి. సో ఇట్ is same. Now again, hence we have to x belongs to he అంటే ఒక్కొక్క కేసు తీసుకుంటాను. What is the one case? First case, x belongs to e and x belongs to f inverse of a, or next x belongs to e and x belongs to f inverse of b. So this is the case. అంటే what is now x belongs to g, g x belongs to e hand అంటే ఏం రాసుకోవచ్చు, x belongs to ఏం రాసుకోవచ్చు, e ఇంటర్సెక్షన్ f ఇన్వర్స్ ఆఫ్ a ఒకటి రాసుకోవచ్చు. x belongs to e ఇంటర్సెక్షన్ f ఇన్వర్స్ ఆఫ్ b ఒకటి రాసుకోవచ్చు. x belongs to e ఇంటర్సెక్షన్ f ఇన్వర్స్ ఆఫ్ ఏం తెలుసు, x belongs to g or x belongs to h. x belongs to h. సో x belongs to g or x belongs to h వచ్చిందంటే మీనింగ్ ఏంటిది, దట్ ఇస్ కాల్డ్ ఇస్ x is belongs to g union h. అంటే x is a belongs to, so that is a g union h. So from x belongs to g union h వచ్చిందంటే మీనింగ్ ఏంటిది, he subset are equal to g union of h. So is double star equation. Star and double star equation we got e is equal to g union h. I am to prove is, so double star equation is completed. So star and double star equation we have to prove. So e is equal to g union h also. Next we know that a bar is equal to a union a bar is a subset are equal to a bar also. So ఇక్కడ కూడా we know that g is equal to e intersection f inverse of a అయితే this is subset are equal to f inverse of a. So f inverse of a subset are equal to కూడా ఏం తెలుసు, f inverse of a complement also. అంటే నాకు ఏమొచ్చింది, దీని హోల్ కాంప్లిమెంట్ అంటే ఏమొచ్చింది, g subset are equal to f inverse of inside a complement. Whole complement of g bar is complement if inverse of a complement is a whole complement. So here from third, f is mapping from x to x to y is continuous. So a bar is a closed in y. So f inverse a bar in closed in y అయితే, so is continuous. A bar is a closed in y అయితే f inverse of a bar is closed in ఏమవుతుంది, x అవుతుంది. f bar is ఇది starting theorem. So is continuous. F inverse is a closed in x. So f inverse of a bar is a closed, c is a closed in y. అంటే ఇక్కడ మనకి ఏం తెలుసు, f is mapping from x tends to y is continuous. c is a closed in y అయితే f inverse of c is a closed in x అవుతుంది. సో కాబట్టి ఇక్కడ a bar is a closed in y అయితే f inverse of a is a closed in x అవుతుంది. సో కాబట్టి the whole bar f inverse of whole bar is equal to f inverse of a bar అని రాసుకోవచ్చు. We are from 4, some 4 equation. Since he is a closed, since he is closed, e closed గా అంటే డెఫినేషన్ ఏంటిది, e bar is equal to he అయితే closed. E bar is the set of all derived set. Okay, the set of all derived set. From third and fourth equation we got, from third and fourth equation is called is, we can do definition from third and 4. So from third and 4 we get the definition is called is, so this is a z bar in subset are equal to f inverse of a bar. F inverse e is a closed quantity. So whenever is a bar intersection b is equal to pi అయితే, this implies a bar is a subset of b complement. So b complement ఇక్కడ కూడా same thing, g bar in subset of f inverse of b complement. b complement. So what is now ఇక్కడ ఏమొచ్చింది, g bar subset or f inverse of b complement అయితే then g bar intersection of f inverse of b is equal to ఏమవుతుంది, empty అవుతుంది. సో a g bar intersection of f inverse of b is equal to ఏం రాసుకోవచ్చు, h is equal to empty. So g bar intersection he intersection of f inverse of b got h is equal, so we got g intersection of h bar. So similarly we can g bar intersection h bar వచ్చింది. Similarly we can prove g intersection h bar is equal to empty also. G intersection h bar is equal to empty is also. So therefore e is equal to, so we got e is equal to, so this is e is equal to g union of h. So g is a non-empty set, so h is a non-empty set, so h is a non-empty set. G bar intersection of H is equal to empty. G intersection of H is bar is equal to an empty set. So therefore, E is not connected. E is not connected. This is a contradiction. And he is a connected set and తీసుకున్నాను. So since E is a connected, therefore F of E is connected set. F of E is not connected is wrong. Hence F is connected. So this is a clear. So this is the last theorem. So in the last theorem of this function. So what is the last theorem is 5.4.3. So 5.4.3, this is the theorem is. So 5.4.3 in page number 5.4.3 in page number 57. In 5.4.3 in page number 57. So that is a found. So a metric space X is not connected if and only if there exists a continuous function of X onto discrete 2 points set 0, 1. Proof. X is not connected, then there exist two non-empty designed open sets A and B. What is the designed open sets? A and B. So X is equal to A union B. So what is the function defined? Capital X tends to 0, 1 is a defined. What is the function defined? F is a mapping from capital X to 0, 1 is a defined by. So f of X is equal to 0. So is equal to 1. This is X belongs to A. This is X belongs to B. So obviously F is on 2. So 0, 1 is discrete metric space. Every subset of it is open. Every subset of it is open. Therefore, 4 subsets. What is the 2 points in upper? What is the 4 subsets of set? What is the subset? Empty set. So singleton 0, singleton 1, singleton 0, 1. These are 4 subsets. F inverse of empty set is equal to empty. F inverse of 0, 1 is equal to capital X. F inverse of 0 is equal to capital A. F inverse of 1 is equal to capital B. So, and all these 4 sets are open in X. Hence, F is continuous. All sets if open in X, F is continuous. In conversely, so in conversely part, this is a conversely part we have to prove. Suppose X is connected, since F is continuous, we have capital F of X is connected. That is 0, 1 is connected in R. This is a contradiction because the only connected subsets of R is R interval. Only connected sets, only real number system to real number system connected set in only interval ఉంటాయి. ఇక్కడ పాయింట్స్ ఏంటి ఇంటర్వెల్ కాదు 0, 1. It's not interval 0. It is the only 0, 1 set is there. Therefore, X is not a connected. X is a connected is wrong. 100% X is not connected. If it is X is connected, the system of a real number, the real number system of a connected set is always a open interval point is there. Because it is there, if it is a given question 0, 1 is a set. It's not an interval, but therefore X is connected is wrong. 100% X is not connected. So we have to prove first one X is not connected. We have to prove F is continuous. Next time X is not continuous and X is not F is continuous and X is not connected. We have to prove. This is a totally, so we part is completed. So this theorem is now again. Oh, okay. All of you, I have to complete this topic is next time is very, very important. You will learn to tomorrow. The topic is every KCL is compact set and also nested intervals and KCL. Tomorrow, every KCL is a compact. Every KCL is compact. So this is a long question. The topic is a unit 6 vector valued function and monotonic functions. Every KCL is compact. Every KCL is compact. We'll learn to theorem tomorrow 6-point learning. So okay. So all of you, my time is over 4:30. So yes, anybody? Any doubts we have to send also in PDF real analysis group. Okay.
Okay, sir.